Yes, madam. Just hold down your pocket.
So let us start today's VIMARSH lecture. And before I start, namaskar and good evening to all of you. Please note that since 2026 onwards, all of our sessions are getting recorded, and we are so you are also recorded. So the good number gives a different representation. So that is why we want the room to be filled. We waited for 10 minutes. So, we are in the process of creating a knowledge repository, because what we strongly feel, myself and people at IIT Indore, knowledge is for the next generation. So that is the reason we write papers, so that other people after us, they can read. So we are making a knowledge repository, and everything will be put in YouTube with a special channel, thanks to the volunteering team. And in addition, all the presentations with proper permission from the speakers we will also put on the web, and the website will be inaugurated today once our director is here, and of course Professor Tanusri is here already. Okay, and just to start the program, as all of you know, this VIMARSH is our IIT Indore's flagship public outreach lecture series, and as the name suggests, so it is VIMARSH, so like which are VIMARSH, right? So that is the way the word has evolved. And thanks to our director, so with a general discussion over the tea, he had chosen this particular name for our lecture series. And all the speakers are advised or requested that they should speak to the level of a general public. Okay, so it is a social responsibility for all of us working at the cutting edge of science and technology to represent our level, of course not really level, at least little science level, which is understandable across the areas. And VIMARSH is something, you must attend, and we should slowly make a culture of attending public lectures. Then you choose your own expert series. But VIMARSH is something which slowly will make a culture at IIT Indore that everybody attends. And I'm quite happy to see my faculty colleagues are the largest in number today. So don't count, okay? So it is largest in number today, and I'm happy that Professor Tanusri Saha-Dasgupta has agreed today to speak as our distinguished lecturer on this series. And before I read out her CV, I think her CV should inspire everyone, including me and all of you. And we expect that next 15 years, we should have at least 10 madams in here, right? So that is the way we should make it. And just for your knowledge, so Professor Saha-Dasgupta works in the area of computational condensed matter, material physics, and now you know there is no boundary, right? So in electrical engineering, I found in biological sciences, okay. And a major thrust of her research is the application of first principle electronic structure calculations to understand the physics and chemistry of novel and complex materials. You see, without reading a priori, so chemistry is coming immediately. So there is no subject boundary as such. And she obtained her PhD degree from Calcutta University in 1995. She was a postdoctoral fellow at Onera, Paris, CNRS, France, Max Planck Institute, Stuttgart, Germany, and then ISC Bangalore. And Professor Saha-Dasgupta is currently a senior professor and director in the S.N. Bose National Center for Basic Sciences, Kolkata. She is a fellow of the American Physical Society, the World Academy of Sciences, the Indian National Science Academy, the Indian Academy of Sciences, the National Academy of Sciences India, the West Bengal Academy of Sciences. She is also a recipient of Sonno Jayanti Fellowship, one of the top one in India, MRSI ICSC Superconductivity and Material Science Annual Prize, DAE Raja Ramanna Prize, P. Sill Memorial Award, Dr. APJ Abdul Kalam HPC Award, and of course the beautiful one is J.C. Bose Fellowship. okay, which everybody dreams. So, and before I go to the today's talk of understanding Earth's interior by computation, I must tell you, if the mathematics was correct, then the universe had to accept the consequences. Do you remember who gave this statement? It is not my statement. So it was told by S. Chandrasekhar, if mathematics is correct, then the universe had to accept the consequences. So beyond a certain mass, a white dwarf star cannot remain stable. After 1.44 times the solar mass, a stellar remnant will collapse to form a neutron star, a black hole, or a black hole. This is called Chandrasekhar limit. If something is mathematically correct, one has to accept the consequences. Computation plays a pivotal role in modern day science and technology, and today's our distinguished speaker, Professor Saha-Dasgupta, will help us explore such a domain of understanding the interior of the earth through computation. So through the wordings of S. Chandrasekhar, so I try to convey the importance of computation in science and technology. So with these words, may I invite Professor Saha-Dasgupta to take over, please. Thank you.
Am I audible? Okay. Thank you very much for this really kind introduction. I don't know, he adjectives that these are appropriate. It's up to you to judge. But thank you once again for this kind introduction and the invitation to come to IIT Indore. So I come from S.N. Bose Center, which is a research institute. And it's a small institute. I'm very glad to see one of our students is now a faculty here. So it's a very different atmosphere. IIT is much bigger, many more young faces. And all the time I come to any kind of such, environment, I really feel my age is also going down. I really feel very young, and I'm so happy to see many young faces in the audience. So may I know how many of you are student? Can you please raise your hand? So, so are you student of science or are you student of engineering? Science. All of you are scientists, mostly. So, when I got the invitation, I was asked to give a very general talk. And I was also said maybe there will be some of the engineers in the audience. So I was in a little bit in dilemma what to talk about. It should not be too technical. Also, it should not be too simple. So this day, I think this has been mentioned by Professor Shahu, that it's an age of interdisciplinary, multidisciplinary. So what I will try to show you, so by training I'm a physicist, but even a physicist can contribute in a domain of geoscience. So in that way, science really has no boundary, as was mentioned, and the same tricks and techniques can be used in many different domains. So that's the title, which has been already said, and our institute, which is funded by Department of Science and Technology. As you can see, that I have also made an acknowledgement to the Ministry of Art Science, because the whole activity came from a project that was given by Ministry of Art Science. And our institute has been basically established by DST to honor the life and work of S.N. Bose. I hope in this room everyone knows the name of S.N. Bose, in whose name almost half of the fundamental particles of the world, namely the bosons, are known. So before I start, as I said, I'm a physicist who is interested in materials, and as has been already mentioned, that I have a special interest on electrons because many of the properties of the materials are basically driven by the electrons. So the properties that you see in the macroscopic level, at the microscopic level, many of the time they are determined by the electrons. So that's one of the focus of my research. And some of these electrons are also strongly correlated. For example, you have bunch of electrons, so like in this room, and if you want to get out of this room, of course it's a very nice arrangement, you may not disturb the next one, but if the room was very crowded, then you have to disturb the next one. And that is a situation where it's called strongly correlated. The electrons are correlated with each other, their motions are correlated. So I have interest on that. On one manifestation of this strong correlation between electrons and the magnetism, I have also worked on if you get into the nanoscale, what happens. And this is the talk which I will give today, is about the arts material. So this started, as I said, I thanked the Ministry of Art Science because it started with a project that was in collaboration between IIT Kolkata and S.N. Bose Center. And this was a project to really look at the oxides and their compounds and mineral phases at extreme condition of pressure and temperature. So it all started with that. And this center was built, which is in IIT Kolkata. It's a national center for high pressure studies. I don't know how many experimentalists are there in the audience. So if you really want to do any of the high pressure study, I think currently the kind of pressure they have achieved with a laser heated diamond anvil cell, that's the technique, and they can actually achieve hundreds of gigapascal. As you know, the arts core is 340 gigapascal. So achieving already some 200 gigapascal is a big thing, and the temperature they can go up to 2000. So that's a very unique facility. And so when I started this thing, I knew very little about this geoscience. It was a completely different world. And luckily this girl, she joined me, and she was a fantastic student who was not at all skeptical to explore some uncharted territory. So when I said, and this was my colleague Surajit Sengupta, was at S.N. Bose Center. He later on moved to TFR Hyderabad, and he had a very untimely death. But Surajit said, Tanusri, let's do something together. And I think this mineral physics is something where we can contribute. So Shostika was a joint PhD student of me and Surajit. And we collaborated quite a bit in the first phase of my talk with Nibir Mondal, who is a geoscientist. So they are geologists, they are really geologists. And Sujay Ghosh from the latter part from IIT Kharagpur is also a geologist. So you see that you can be by training anything, physicist, chemist or anything, but there are so many young people, your horizon needs to be big, that your science is science. I think our biggest example of this country that has produced such a thing is J.C. Bose. You have all your thing. J.C. Bose never thought of anything. So he, his nomination to the Royal Society, he became FRS at much later age. Because they could not decide Royal Society whether to put in physics or in biology. What he is, no one knows. So, but you see, our country has produced something. S.N. Bose, the institute from where I come from, S.N. Bose, to start with, his master's degree was in mixed mathematics, which these days are called applied mathematics. And then he worked in a field of theoretical physics, right? The quantum statistics. And for his, he took a study leave from Dhaka University. He was a reader there. And he went to a lab to learn about crystallography, which is an experimental physics. So you have to see a same person can actually do a lot of things. So given this background, we are back to art. And as you know that art, you can peel off art, and there are different layers. And these are these different layers, which is the art's crust. So my talk, I will focus on some minerals which you can find on art's crust in the first part, and in the second part, I will talk about the inner core. Somehow I think that this pointer, No, because it's So I will probably, I think I will show with my finger, that should be enough. So in the last part, I will talk about the inner core. So in between the crust and inner core, as you may know, is solid, while the outer core is molten, and there is a dynamo effect because of Earth's magnetic field, and that's because we all are here. So, you know, this is such an interesting thing. But these are all very macroscopic things. But many of this behavior actually are governed by the electrons. So we used some theory to understand the behavior of the electrons to this Earth's material. Because electrons, the glue that binds atom together, bonding, everything arises because of electrons. So quantum mechanics action. These days you all talk about, you know, quantum science and technology. So quantum mechanics is in action even to understand Earth, which you think it's a big macroscopic thing. So I use the word first principles. I think many in the audience may not have heard the word before. So it's a first principles approach, because for this calculation, as an input, you don't need to assume almost anything. So that's why it's called the first principles approach. And it gives a way of calculating properties. So for example, if I really have to do an experiment, Earth's inside, no one can dig and find out, right? So the only thing people can measure, I will come later part, is density and the sound velocity. So you have very few limited information about Earth. So to model this thing, computation is actually a big helping thing, because almost nothing can be measured. In the lab, getting into that kind of condition is extremely challenging. And I will come to also some of the difficulties when you are inside the lab. So this is basically a first principles approach. As I said, you almost don't need to assume anything. All you need to know what it is made out of, that's composition. And you need to know the structure. These days, even the structure can be calculated. And knowing that, you get into the properties. And this is inside what is there. So how many of you are a master's student? I think mostly all of you. And are you a student of physics, chemistry? Physics. So you all know Schrodinger equation. Can I assume that? Okay. So all you are doing, you are basically solving a Schrodinger-like equation. If you see this equation, it is pretty familiar to you. It's like a Schrodinger equation. But there is a, think of your harmonic oscillator problem or your particle in a box problem. There the V actually had only dependency on the space coordinate, nothing else. That's why you can write it as a time independent Schrodinger equation, doesn't depend on time. But here what you have, that this potential depends on something which is called rho. Rho is nothing but the density of the electron. So how do I define a rho? If I know the wave function, I take the modulus square and I get into density. So you can see that the psi here is actually an output. This wave function is an output. If I solve the Schrodinger equation, then only I will know the wave function. So that's an output, and potential is normally the input. So the input here actually depends on the output. Have you faced any such situation before? If you are a master student? No? Have you faced such a situation where the output depends on the input? Huh? Hydrogen atom potential is known. Hydrogen atom, I know I have really this spherical potential, and therefore I have basically a partition into radial part and the angular part, and I solve it. That's not the case. No, you have gone too far. I am just talking at the master's level. Have you ever heard of any situation, all your master course, have you ever heard of a situation where your output depends on the input? Rather, the input depends on the output. They are connected. No? Yes, but in any equation, have you solved the Ising model problem? Yes or no? You have been all taught Ising model. If you write the magnetization, you actually lead into such a situation which is called transcendental equation, right? So, one of the procedure of doing it is an iterative method. That means I assume a form of the potential and then I solve such kind of equation, I get the density, and once I get the density, there is another very famous equation, Poisson's equation. You solve that Poisson equation to invert the problem, and from density you get to the potential. And you iterate it until and unless I actually find the density in this iteration and that iteration, they are less than such value. And then how much is the tolerance, it's up to you. So that's the basic thing. All we are doing is basically solving two key equations and iterating between them. So what are the things you can do this way? You can calculate the total energy of a system very accurately, and from there you can get what is known as band structure. Some of you may be knowing the band structure. That just tells you how an electron disperses in a crystal. If it is a crystal, I can define, because there is periodicity, so I can define a wave vector, and then how energy varies as this wave vector, that's called a dispersion. And that's also called a band structure. If you have such a thing, you can actually define all the optical transition and you can get to the optical properties. All of these are actually zero temperature calculation. Since many of you are masters in physics, you know what is a phonon, lattice vibration. So if you can calculate the phonon, you can calculate the phonon, because I can calculate the total energy, and therefore with the displacement of the ions I can recalculate those energies, and therefore then that gives me the dynamical matrix, and if we diagonalize that dynamical matrix, I get into the phonon modes. So if you know phonon, you can actually calculate the Helmholtz energy and the Gibbs-free energy. For the Gibbs-free energy, you need a little more information. You also need to calculate by changing the volume exactly how phonon changes. But phonon you can calculate, and therefore in some way you can have an access to free energy. These are important because these are not zero temperature. Earth is not at 0 Kelvin. Earth is at finite temperature, very high temperature. So I need to include temperature. The other way of doing temperature is where you unify quantum mechanics with classical mechanics. How I can do that? So electrons, they are quantum object, and I already said you have this equation which looks more like a Schrodinger equation. So I am using quantum mechanics. But the ions, they are much heavier compared to that of the electrons. So they can be treated as a classical object. So therefore, you can then do something where how the ions will move, that will be decided by classical Newton's equation of motion. And if that is Newton's equation of motion, then where from my quantum mechanics is coming? So these ions will move under some force, and who creates that force? Electron creates that force. So the force therefore is calculated in a complete quantum mechanical way. So you can see you can actually merge classical mechanics with quantum mechanics if I have to affect a finite temperature. What the finite temperature is doing is basically displacing all the ions, and the ions have started moving. How they are moving? Depending on the temperature, I have a temperature scale. So in the Newton's laws of motion, I will have those forces which will be given by these electrons. So that's actually a way which is much more expensive computationally, but better way than going through Helmholtz or Gibbs free energy. So now I come to minerals. So do you know what is Earth's crust made out of? Silicates. They are all silicates. You have mica and all that. They are all silicates. So they are basically silicon surrounded by 4 oxygen, giving rise to an SiO4 tetrahedra. It's a tetrahedra. If you take the radius of silicon 4 plus cation and the radius of oxygen and ion, then you can see that the most compact you can get is actually a tetrahedron. And there are various kinds of silicates. Inside the mineral, you can have isolated this silicon oxygen tetrahedra. They can form like a ring, as is shown here. They can also make a framework, as you find in quartz. You can also get, these are in mica, I mentioned of mica. So, and they are something where they form like a chain. There can be a single chain, double chain. So all of them are distinguished in the way this basic unit is connected. And you will find all of them present in Earth's crust. So the first problem we did long back was this mineral is known as olivine. And you can see there is a very nice olive green color. That's why the name olivine comes. And this is formed by this isolated blue colored silicon oxygen tetrahedra. Since it's isolated, there are voids. And these voids has a shape of an octahedra. An octahedra is one which has 6 oxygen making a coordination. And what happens, a metal atom goes and sits in that void. Okay? It's mostly magnesium. In fact, Earth's crust has a lot of magnesium. But if all these octahedra was filled with magnesium, the color of this mineral would be white. People have made it in the lab, and that color is completely white. The fact that it is olive green is because there are some amount of iron that is present that gives it the olive green color. Otherwise, it would have been completely white. Now, the big question is that in these octahedral void, there are 2 kinds of octahedra. There are octahedra M1 and M2, which is marked there. Volume of M2 is larger than the volume of M1, and these octahedras are distorted. So M2 is much more distorted compared to M1. So that's the basic thing. So the problem is, if iron goes, which site iron sits, at M1 or M2? That's called the site preference problem. And what we thought of doing, experimentally it's very debatable. If I have olivine, which site iron goes? There are different experiments. One says they go to M1 site, another says they go to M2 site. But pyroxene, which is another mineral I just mentioned, have a chain structure. There they know for sure that iron goes and sits at the M2 site. So we said and no one has done computation before us for this problem. So we said we will first do the calculation for pyroxene, for which experimentally it's known iron goes and sits at the M2 site. If we can reproduce that, then we will know that we have a right computational framework, and then only we will apply it to the olivine problem. So these are the 2 minerals, one is olivine, another is pyroxene. If you go inside it, their structure looks very different. Now, if you calculate the energy, you can calculate the energy. As I said, we can calculate total energy very well. You put iron once at the M1 site, another at the M2 site, and we do find that indeed for pyroxene, iron has a very, very strong preference for the M2 site. And repeating the same thing for olivine, we find it reverses and iron prefers the M1 site. This is the result of some calculation, but you have to interpret it. You are a scientist. Why does it happen that way? So, if you have olivine and pyroxene, in case of the pyroxene, M2 is larger than M1 by 3 times and is much more distorted, but distortion is larger by 3 times. The size difference is 17%, while for olivine is much less, is 5%. So, you can see that when it is 5%, you are really at the border, and that is where you know things becomes much more interesting. So, if you look at the ionic radius of magnesium versus iron is larger. So, by mere size consideration, you will think that iron will always go to M2 side. So, why it is not the case? There is something else also which is known as how delocalized the iron is. So, for example, if you have studied quantum mechanics, the electron can be in the form of a wave, right? Now, is this wave packet localized or delocalized? If it is really very delocalized, then the electron can gain kinetic energy because the electron can move from one side to another side. You can have a particle-like picture, you can also have a wave-like picture. If you have a wave-like picture, it means that the wave packet is delocalized and it is spreading over many sides. So, that gives a gain in the kinetic energy. So, it so happens that in case of olivine, if iron is sitting at the M1 side, there is a gain in this kinetic energy, which overcomes the size effect of only 5%. In case of pyroxene, because of the change in the crystal structure, the gain in the kinetic energy is much more if it sits in the M2 side, and it goes then hand in hand also with the size effect. So, in case of pyroxene, these two effects, kinetic energy gain and the size effect, they both prefer M2 side. In case of the olivine, which is really at the border line, the gain in the kinetic energy overcomes the size effect thing. Now, these are all at the 0 temperature. All our calculations were at 0 temperature. What happens at finite temperature? You can see a list of experiments. So, some of the experiments says as the temperature increases, the side preference, there is a crossover. So, the iron which preferred the M1 side, with the increase of temperature, it now prefers the M2 side. Some other experiment, they says no, it remains in the M1 side. So, given this controversy, we also looked at the crystal structure data. So, there are crystal structure data measured as a function of temperature, and there are 2 sets of crystal structure data which is shown with the 2 different color. And what we find that if we take the volume difference between this M1 and M2, which is the size effect, most important effect, for one of the data it does not show any change. For another data which is with the brown color, around 600 or something, there is indeed a dip. So, maybe that is what is making it change. Then what we did is the following. So, I think I mentioned Ising model. So, all of you have studied Ising model? Yes? Okay. So, that makes my life simpler. So, you know, I can actually think of, if I have 2 species like A and B, I can think it like a up spin and down spin. So, it is not a real spin, it is a pseudo spin, but I am casting these 2 species A and B as 2 orientation of the spin, and then I can use the technology of my Ising model. So, what is done here, the magnesium and iron, which are 2 species which we are interested in, we are saying they are like up and down spin. And then what I have written, those who remember the Ising model, it is more like the Ising model. So, these are the spins, but not real spin, these are the pseudo spin. So, there is an exchange between the spin and different exchanges, nearest neighbor and next nearest neighbor, like this J1 and J1 prime. And then I also have something which is called the H, which gives basically the energy difference between iron and magnesium. So you see what computational, as a computational person, what we are doing. We are modeling this complex problem into an Ising model like problem, because I am dealing with only two species, iron and magnesium. And then HS is very important, which gives me the site preference, whether the iron will sit at the M1 site or M2 site. So this is like your Ising model problem, but I have made it little more complicated and catered to customize to the problem that I am looking at. And I have made the spins like two species, because in an Ising model, I have only two orientation of the spin. So if you basically now solve this problem, and that's where all our quantum mechanical calculations were important. By doing quantum mechanical calculation, we extracted the values of the J1, J1 prime, which are the parameters of this Hamiltonian H and HS. And then, since it's a Monte Carlo calculation, we did a Monte Carlo calculation. So how many of you have heard the word of Monte Carlo simulation? Quite a number of them. So this is nothing but, so this was devised by von Neumann and Ulm during the World War II, during the Manhattan Project. It's like throwing a dice and with a certain probability. So that's all you are doing. In our case, you have a temperature. So you have a Boltzmann factor, right? I'm going by the Boltzmann statistics. And depending on that, whether the move will be, whether the upspin will be downspin or will remain as upspin. That's the probability. And you run the entire thing with that. And doing that, after you have really equilibrated, meaning your free energy as a function of your simulation time should be in a converged situation, then what you can calculate is what is known as distribution function. And this distribution function, if it is greater than 1, just from the equation, then iron prefers M1. If it is less than 1, it prefers M2. And if it is 1, iron is completely randomized between the site M1 and M2. And what we find, that is our result, that there is no such, with temperature, no such crossover. So that means the other set of experiment got our support, not the previous one, which were more with this neutron. And we found actually why. There was nothing wrong with the experiment, but there was something wrong in the interpretation, which site it will it will sit. They tried to extract it from some thermal expansion parameter, and that had the flaws. So I'm just trying to impress on you that how computation can exactly help, even with the experiment in such kind of completely different topic. I didn't intend to even work on this topic. So then I think I will try to hurry up a little bit. So now all of these, where you assume your mineral is perfect, but it's actually not perfect, especially when all these minerals are formed. Depending on their formation condition, you actually have some vacancies, missing sites. And depending on which condition the mineral is formed, there can be plenty of vacancies. And any naturally forming mineral will have those vacancies. Now, once you have this vacancies becomes mobile, right? They will move from one side to another. There will be a diffusion of those vacancies. So how do they really change the properties? Okay? More important is, experimentally, you cannot see vacancy. You cannot measure them. It's an absence of something. So how do I measure it? In fact, there are some experimentalists in this audience. If you ask them how much percentage of vacancy you have, do you have an answer? No. You can't measure vacancy. You don't know. You possibly know there are some vacancies, but you can't estimate how much is the percentage of vacancy other than doing some chemical analysis and you will find that that much percentage of some chemical component is missing. So possibly there are some vacancies. But if I ask you to track the vacancy, will you be able to track the vacancy? So we thought about this problem, and what we found is the following, that vacancy is most easily formed at the M1 site. And not only that, in presence of iron, this vacancy formation energy is hugely reduced. That means if we have iron, the vacancies are much more easily formed. Now, why is that? Any idea? Any wild guess? So, at M1 site, either I will have magnesium or I will have iron. So, that means absence of some magnesium or iron. Right? Now, you remember that iron is a transition metal while magnesium is not. That means, by definition, a transition metal can have multiple valences while the magnesium cannot. So that is what it is. In case of magnesium, you have a charged vacancy. That means if I pull out that magnesium, I'll have a pile of charge sitting there. And that is expensive from electrostatic point of view. On the other hand, if I have iron, if I remove an iron 2 plus, the neighboring iron changes to iron 3 plus to accommodate the absence of a iron 2 plus, because iron can change its valency. So if I have iron in the system, the biggest change that happens, that your vacancy becomes neutral as opposed to a charged vacancy. So that reduces, gives a significant reduction, if I can show the thing. So these are all in electron volt, huge amount of energy, and you see only with 12.5% iron is strongly suppressed, this formation energy. So what we found with our total energy calculation again, the vacancy most favorably forms in the M1 site, as I have already mentioned, and the iron neighboring to this vacancy site, which is shown here, you can see the chain-like structure, that transforms to iron 3 plus from iron 2 plus, and iron 3 plus prefers M2, unlike iron 2 plus, which prefers M1. So iron 3 plus prefers M2, while iron 2 plus prefers M1. Now, once the vacancy is formed, the vacancy has to migrate, it has to diffuse. And to diffuse, it has to overcome a barrier height. So it can diffuse in many different paths. We did all the calculations and we found that vacancy wants to diffuse in a vertically in this crystal, as is shown here, and this is the diffusion barrier. So from here to there, this is the initial configuration and this is the final configuration, and they have to cross a barrier, and that barrier height we estimated. And what we found that whether we have iron or no iron, this barrier height is kind of similar. So what actually the energy required for vacancy diffusion is actually contribution from two. One is from the vacancy formation energy that is highly affected by presence of iron, and the barrier height, which is much less affected by presence of iron. And now we complicated the Hamiltonian, Ising-like Hamiltonian that I have showed you before. Now it is not spin half. If it was spin half, I will have plus half and minus half. Now I have three species. So three species is iron, magnesium and vacancy. So then I have to consider a spin 1 system. If I have a spin 1, then the corresponding states are 1, 0, minus 1. So I have 3 states. So instead of 2 state, now I have a 3 state Ising model. And as you can see, the Hamiltonian looks much more complicated. And then we did the same molecular dynamics, and the result was fascinating. we looked at the wrong iron site. What is a wrong iron site? So I have a vacancy which is trapped at the M1 site. The site next to this vacancy site is iron 3 plus. Now the vacancy moves, as soon as the vacancy moves, this iron 3 plus for charge balance changes to iron 2 plus, but it is stuck in M2 site, which is not the preferred site for iron 2 plus. So that means as the vacancy moves, diffuses, it creates a trail of wrong sites. So it is like, you have a criminal who entered inside and has done some crime. The criminal has left, but has left the traces of it. It's exactly that. So this is for some small time scale Monte Carlo, for longer time scale, and you see this trail of the wrong site it creates. And we said that, your crystal is not perfect. Maybe to start with, there was some randomization between M1 and M2. That is the situation. But even then, you can identify this trail, because this trail is very, very directed, extremely directed, because iron always, vacancy always prefers this M1 site. And there is a certain trail of this M1 site. And since the wrong site follows where the vacancy has moved, so it follows exactly that trail. Now, how an experimentalist can actually now detect this? And apparently such thing for the oxygen vacancy was done for cerium oxide. No one has done it in this mineral. So all you need is you have to make a distinction between M1 and M2 site. So if you have a high resolution transmission electron microscopy, you can basically resolve between M1 and M2 site. And then I need to resolve between whether it's iron or magnesium, and for that you can have electron energy loss spectroscopy. So no one has done this experiment, but this is what our prediction is. If you can manage to do this experiment, actually you will be able to follow the path the vacancy has moved. Should I finish, or I can? Okay. So, so far I was in arts crust. Now I will come deep into the arts inner core. I really make a jump. Now, a big thing is what arts inner core is made out of. It is known that arts inner core is made out of iron, but iron in which form? So normal iron, which you know, is in which crystal structure? Any idea? I hear BCC. Who said? Someone said. So iron is BCC, but if you take the BCC thing, there are some discrepancy. So people thought that iron in this inner core condition is an hexagonal close packed. Body centered cubic is quite open structure, while hexagonal close packed is much more compact. So under this inner core condition, I really have a very dense situation. So people thought that will be like a hexagonal close packed. So that has a problem, that has a much higher density than what is measured from some geophysical model. As I said, only 3 things the experimentalist can measure. One is the density, and the other quantity is the sound velocity. So there might be possible presence of other elements. Other light elements can be anything, can be carbon, silicon, sulfur, oxygen, hydrogen. And if you can really crack this problem, you will actually have a nature paper. That much I can guarantee you. But the problem is then the computational people, they try to do, of course, various kinds of model, and I will show at least 2 of them we have predicted. And then they try to fit it to the density and this sound velocity. So one of these is iron has a very high cosmic abundance, carbon, And from the other planets, that the Earth's core took place from a magma ocean that is also surrounded by hydrogen, helium, and carbon-rich atmosphere. So meteorite that comes from the other planets, that composition the scientist has analyzed, and they are mostly iron carbide. Now, even with the iron carbon, there can be various possible compounds. So one of the compound is iron 7, carbon 3, and even that can have two different structure, an hexagonal structure and an orthorhombic structure. And what we did, we basically carried out, I mentioned about two free energies, if you remember at the beginning. One was the Gibbs free energy and another was the Helmholtz free energy. So we have basically the Helmholtz, which is like this enthalpy. So we found that all the time actually this the one that was basically always favoring is the hexagonal phase, but then you have problem with the density, and then you have to assume something which is like silicon. So on the basis of the deep magma ocean in the core formation, it's suggested that the core contains also some 2 to 8% of silicon, and we assume some silicon, and we found that the silicon actually replaces the carbon, and in the silicon we found now the orthorhombic phase becomes stabilized, and what is being calculated is the sound velocities, which can be two different. You can have a longitudinal wave, you can have a shear wave, and you can also calculate the Poisson's ratio. So you can see all of them are related to nothing but bulk modulus and shear modulus. And you have to calculate it as a, of course, at the Earth's condition of pressure and temperature, which we did. And then we also plotted it as a function of density. And these square points, these square points are actually the experimental data. And we do find that if we consider with this silicon, this iron carbide, it has almost very close to the experimental data. But then there is this catch that you have only 3 unknown and you are trying to fit all different possibilities. I'll finish with only one other possibility. As you can see that Shujai, who is a geologist, is one of the authors here. Also the previous one had Shujai. So where we said that how can you stabilize BCC iron at the Earth's core condition, and then we found that iron, in addition to iron, if it has some nickel, then that can stabilize the BCC phase of the iron, and that can also explain all the sound velocity Vp and Vs that I mentioned, as well as the density. So is it BCC iron with some bit of the nickel in it, or is it really the iron carbide with some silicon in it? We don't know, because these are just different proposals, and further experiments are needed really to understand what is the composition of the Earth's core. So I think with that, I hope that I could convince you that computation is a useful tool to understand many things, but including also Mother Earth. Thank you very much for your attention, and if there is a question, there are some questions, I'll be happy to answer.
Maybe I can just...
Yeah, please, I can hear you.
Yeah, thank you so much for a very wonderful talk. I was just wondering, because in the core of the Earth, you have very high density of electrons. Since you are trying to model the electrons using a density functional theory, have people tried to do it using a continuum approach, let's say a fluid approach, and vis-a-vis DFT and fluid approach, which one is better to solve your problems?
It's a very good question. In fact, in the fluid approach, the problem is many of the atomistic details that you are considering, it will be very difficult to tackle with. But the question you asked is actually very pertinent, that within density functional theory, it's actually a mean field kind of approach. So, in this high density, is a mean field approach a good one? That's a very valid question. People have tried to go beyond mean field to deal with arts core. They have found some success and there are some papers. The major problem is these calculations are very expensive. So, if I go beyond mean field, then I am adding another layer of complexity, and that makes the calculation almost prohibitive. But there are indeed few papers where they have tried, especially looking at this dynamics of this magnetic field, that has been tried with going beyond mean field. Correct. In fact, many of these, these are little technical, there are Wilson ratio and all that, that actually shows a very non-trivial behavior when you go into arts core. But it's a very, very pertinent question. I think students should ask question. This is supposed to be very general. No, no, please, please, please.
So that was very interesting that you can trace down the movements of the vacancy. I mean, even in oxides we see oxygen vacancy.
Absolutely, it's similar. Absolutely. That's why I showed the example of cesium oxide. There people have used exactly the same kind of thing, and they could trace actually the path of the vacancies.
So I have this question, since it is moving and locally you see the valence state is also changing. So surrounding will change, right? And that may create some kind of defect in the
Yeah, you are also very right, because the size of M1 and M2 being different, that is what we said is a wrong side. It's actually more like we made the problem much simpler, right, in a coarse grained scale. So, when I say a defect side is just not only iron 2 plus in a wrong side, but it's also deformed, highly deformed, because their size are different. Iron 3 plus and iron 2 plus sizes are different. So, if it is sitting on a wrong side, it will also deform the thing. So, there will be also local deformation. So, for example, this one which I said that with a high resolution TEM, you should be able to, high resolution TEM people actually have could differentiate between M1 and M2, their sizes are very different. So, that they can. So, first thing is to really look at this defected thing, but then you have to ensure that the iron is sitting there. That is why I talked about the electron loss spectroscopy. So, I need to be sure that the iron was there. So, there are two things, but indeed there will be a deformation of the crystal, structural deformation, yes, correct.
so phonons may get affected probably.
Lot of things can get affected, but you need a local probe, right? If you think of anything which is global, that will not serve your purpose. You need a local probe. So, that is what I am trying to get into. I have to locally basically scan the thing that it is moving. It is a local probe needed. That is why I said electron loss spectroscopy, which can locally get the thing. We need a local probe. And phonon might get affected. You may get, it is a global thing. Yeah, exactly.
Hello, ma'am.
Yes.
I have a question that you have Hamiltonian written there. Why HS is same for both M1 and M2 site you have taken there?
Sorry?
HS, that site preference coefficient you have taken same for M1 and M2 site in Hamiltonian.
Maybe I will go back. I will go with the simpler one.
Yes.
Is this Hamiltonian?
Yes.
Yeah.
HS.
Where? Yeah.
Why HS is same for both M1 and M2 site?
HSE is not same. HSE gives me, see, this is SI which I am taking +1 or -1.
Like
right?
why you have taken
HSE is the difference between M1 and M2. It's difference, it's not the same.
HS indicate the site
HS.
preference. Yes.
HS is actually the difference between M1 and M2. Look, I am just summing over all M1, right? And I am summing over all M2. Suppose there was nothing in the M2. So this whole thing then will be actually giving me 0, right? And then this one is 1, this will give me HS, correct? If all the ions were at the M1 side, it will give me HS. If all the ions were at M2 side, it will give me minus of HS. Do you get my point?
Okay.
See? So it is, we have written in such a way so that HS captures, if it is at the M1, it will have one sign of HS, plus sign or minus sign, and it will have an opposite sign if it goes to M2. That's how the Hamiltonian has been written.
Thank you.
Ma'am, here you have calculated the Helmholtz free energy along with the Gibbs free energy function. Generally, we are calculating the Helmholtz free energy for the determinations of the mechanical work. Here inside the art core, which kind of mechanical works are going on?
No, so the point is whether you have a change in the volume, you have in a constant pressure, and you also have a change in entropy, right? So when you are saying Gibbs free energy, your temperature is in action and your entropy is changing. When you are talking only of the Helmholtz free energy, then your temperature part is not there, but since I have a pressure and my volume is changing, that's the work getting done. So it's P times delta V, vis-a-vis T times delta S. I think he wants to, he is.
I have question regarding the structure. Since iron is VCC and we account the high
No, that is the point.
Yes, ma'am.
Iron is BCC under ambient condition.
Yes, ma'am. And
So if you have a completely different pressure temperature condition, that's the question.
Yes,
Will iron remain BCC? The answer is iron will not remain
yes, ma'am,
BCC.
it's changed to the structure which optimize the condition in which high pressure, so it's reduces volume.
Yes.
So it changed into SCP. What about temperature? Because in in that time the temperature also high. So
Yeah,
we need to-
so it is not only your pressure is changing, your temperature is also changing, and in that temperature and pressure condition where my volume is highly reduced, is much more favorable for iron to take either a FCC or a HCP, which are both close packed, compared to BCC. But if I consider only iron and take this HCP or FCC, then the density they measure, the experimentalists, is not matching.
Because ma'am, in SCP and FCC there is also difference of packing. ABC.
Yeah, absolutely correct. In fact, they are very competing, but neither just HCP, pure iron is not the solution. That's first thing. So if I assume HCP or FCC iron, in addition to iron, there should be some light element which will reduce my density. That's one answer. The other answer is, indeed the BCC becomes stabilized, but in presence of something else, which I showed the second route, where I said if you add some nickel, there are some local distortion that makes even BCC iron stabilized in that condition of temperature or pressure. Which of this route is correct? We don't know. I hope I could answer.
Any more questions? Any other discipline? Chemical engineering? Physics?
Yeah, so actually ma'am, I have a basic doubt. So you said that while calculating this diffusion, so if you compute this, means if the surrounding conditions are same, then can this problem be solved hydrodynamically, that I can just see the
No,
flow?
the surrounding condition is not remaining same. That's the issue. Because when this vacancy is moving from one side to another, then in the original position, that surrounding has changed. And here, locally, which was a different surrounding, now has to change. So it has to dynamically adapt to it. So conditions is not keeping same, right? And that's why we need to bring some, I think the question that was asked, can I have a continuum model? So if I have a continuum model, your question is kind of related, then all these details of the atomistic I am missing. And as it looks like, these details of the atomistic is important, because iron 2 plus changing iron 3 plus is fine. But then I am also bringing some structure, like the kind of question she asked, because there is a size of this octahedra which is also changing. Then if I have a continuum model, I won't be able to capture those things. And whether it's a magnesium, whether it's iron, because it's a complex multi-component system. So therefore, having a continuum model probably is difficult. I'm not saying it's impossible, but an atomistic model is preferred because it's a multi-component and your environment is also changing. It's a changing environment. Environment is not remaining same. So wherever that was our clue, wherever the vacancy is moving is changing that environment. And that's why I can detect it by following the environment. What we were doing, we are not doing vacancies, following vacancies. We are following the changing environment.
So looks like there is no more question, and we can continue the discussion during tea time. Okay.
Yeah,
So,
if you feel, and also you can write me
yeah,
email.
so comfortably you can discuss, and also you can talk to her.
Yeah, you
What are
can
the
write
career
me email,
opportunities?
most of the time I
Yeah, so
respond.
some people wanted to discuss about career opportunities in computational.
Oh, okay,
So
sure.
maybe during tea time you can discuss. Okay, so let's give a big hand to Dr. Tanusri. And now may I invite our director just to have few words and then felicitate Professor Tanusri.
In today's scenario, I think I missed a very important lecture. You know, what is there in the inside the earth, and you know, everybody is actually eyeing the place where they can dig and take out the minerals and so many things. So I think your work becomes more and more relevant in today's day. So thank you very much.
Thank you. Thank you.
It seemed to be a very interesting topic, and I missed it. Sorry about that.
No, you have also, maybe I will get down.
So many things, but I really missed the talk. I think he has been
He is a fantastic host and
whole thing
fantastic organizer.
Exactly. So thanks to you also, Ravina.
Thank you for making it.
You can do it.
Should we go to the dad? So he is requesting. Okay.
What is this rupee sign here on the first?
It's money is given by this too. Money is so important. Otherwise we won't be able to do anything.
We realized yesterday.
Thank you.
you very much.
Thank you so
Thanks a
much.
lot.
Thank you. You should also come in the picture. Thank you. Thank you so much. Thank you.
So I think it is a better opportunity for which we have been waiting since long time to launch the website of Institute seminars and outreach. So may I request both the directors. So I think there is a link on the main page.
Yeah, he is the host of everything. Where it is? Outreach.
Just click on
Outreach, yeah.
And then
Yes,
Done.
th-
Over.
That's over.
You can also click.
So then I will
So-
tell you.
We can go to about.
Okay.
So that's a note from director. And
Yeah, scroll down. Yeah.
that's a committee member. I
And,
met.
since Professor Saha-Dasgupta is here, so I think all the messages from director. So you will find this message is little different. I don't know if you can recognize that, but I could recognize that. So we should actually congratulate him in an official manner for becoming the fellow of INSA, New Delhi. So that we have added to his profile.
Congratulations. Congratulations.
And then if you scroll down, so of course the committee members, and that is not important. What is important is we have started making
the
a
events.
repository.
Yeah.
So we will put all these resources, like this event is recorded, so it goes to YouTube
You have
tomorrow.
to take their permission.
Yeah, yeah. So
Then
That
only-
he-
written permission we are taking, and then all the PDF or PPT files will be here. Okay, and then it lists all the talks. So whatever we have done, and some more will be added with picture gallery. Then most important thing is there are lots of activities going on at different departments.
I see.
So what we are doing is, so this will be linked to the
All the
outreach
departments,
page, because nowadays this institute perception and ranking, so this is a big parameter, so which we thought this will contribute. And with this, may I request the student team, because student team is very important. Of course, I have spent time in correcting,
Okay.
but
okay.
they made it happen.
Oh.
So that was a dream for a year, and we are not getting proper platform to launch it. And you may be surprised, our chemical engineering students, so they came up. So
great.
can you please come on the dais and then,
Yeah, please.
okay, so this is the student team. So they helped us building up our perception.
Thank you. I think you are doing other websites also.
Priyansh, please come, Priyansh.
I see. Thank you. We are actually designing the whole website also. Some new design will come.
Very nice.
Thank you.